You're all set to go.
Thank you very much, and good morning, everyone. So again, my name is Gilad, and it was a long introduction. Almost half of my time was just introduction. I'm going to go and review a little bit what Mellanox is doing in the field of high-performance computing, and then some of the developments. I'm going to go throughout several development areas that Mellanox is working on. Hopefully you find it interesting. If you'd like to first work with Mellanox on several development, then please catch me during the break. I think there is a 10:30 or something like that. So a little bit of a background. Mellanox is a company that develops high-speed interconnect solutions where the focus is to develop those elements for high-performance computing. We do sell those products into more places such as cloud and Web 2 and database and storage. But the main reason is because those areas started to leverage more and more high-performance computing products and capabilities in order to build scalable infrastructures. So Mellanox do everything from connecting PCI Express to PCI Express in the sense that we develop silicon devices for both adapter cards or NICs and switches. We build the cards in multiple form factors, switch, software, cabling infrastructure. Last year, we added another product line into our offering, which is called Metro X, which enables to extend RDMA or high-speed interconnect solutions to around 80 kilometers. So that enables to connect multiple sites on campus, for example, to form one single clusters or a cluster that can be used for multiple things. Mellanox solutions are being used today for half of the petascale systems in the world. I think in the previous slide there were a couple of systems. Supermock is one of them in Germany, and it was another, I think, couple of more. But from the 40 petascale systems in the world, Mellanox is connecting half of them. I think the next one is connecting 25%. So a solution that is used in many of the systems today. One example, and this is one of the largest known cluster, I would say, in the world that runs a single application over that size. There are 20,000 nodes in a single system in NASA in Tel Aviv, California. That system is being used for climate research and others, but it's a great example how leveraging off-the-shelf components and taking high-speed interconnect enables people to build very large and scalable infrastructures. There's many more examples, and I'm trying to be kind of simple here, but leveraging HPC would pretty much make the world a better place and a safer place. Right? HPC changed, for example, the automotive industry and helps people to develop much safer cars and much in a fraction of the cost. But there is other examples, and I wanted to pick this one. This is a case of companies that develop solutions for doing genome analysis, and it's part of cancer treatment. And the way that it works is that they bring patients and do analysis, and then taking all the database that they capture, trying to work on it and try to figure out what's the next step for treatment those people. They typically had to work on their database or the data that they capture for 7 days before they could bring a recommendation. And then moving to HPC components, they were able to reduce that time to 1 hour. So that's a great example of how HPC technology helps to make the world a better place in many, many areas. So it's not just the research elements, but it actually making things much better for everyone. And there is more cases where HPC is changing the way that people work. PayPal moved to use HPC for fraud detection. So they have several thousands of nodes where they're utilizing HPC and high-speed interconnects for doing that. Microsoft Bing Maps is doing all the mapping based on HPC technology. Supermarket chains, in order to understand the habits of buying and try to do the right programs, are doing the same. And there is many, many other examples. I'm going to skip this one. It's definitely as well on cloud infrastructures. Now, the reason, or the main reason why high speed or low latency interconnect makes a difference, you can look on the top 500 list, which lists the 500 most powerful supercomputers in the world. and look on the efficiencies of those systems. And from that, you can really understand the benefit of high-speed interconnects. And this is why Mellanox is focusing on that area. The graph here map all the 500 supercomputers on the list according to their interconnect capability and then according to their efficiencies. And you see that gigabit Ethernet is around 50%, or enable 50% efficiency, which means half of the system is pretty much wasted. Moving to 10 gig per second, that's increased the efficiency of the systems to around 65% in average. The Cray interconnect, for example, take the systems to around 80% efficiencies. And then moving to InfiniBand, with InfiniBand, people were able to build systems with almost 97% efficiencies. So that's a great demonstration how you can build with off-the-shelf components and standard components a very high-speed, a very scalable and efficient infrastructure. Now it's not just taking the lean pack from the top of fund and looking at the efficiencies there, but the multiple cases of application. There are 3 cases here of comparing CFD, oil and gas, and bioscience application, and looking at the differences between different interconnects. At the end of the day, increasing the speed, reducing the latency, and doing more offloads definitely greatly impact the performance of application that you can achieve on clusters. From roadmap perspective, today Mellanox delivers 40 and 56 gigabit per second end-to-end solutions. Other companies are trying to bring right now 40 end-to-end. I don't think that no one else has 40 gigabit per second end-to-end. We released the 56 gigabit per second in 2011. We started to work on 100 gigabit per second. And we plan to release 100 gigabit per second in the 2014-2015 timeframe. So as we move forward throughout the year, we're probably going to do further announcements around that. And then beyond the speeds of 100 gigabit per second, they already started to work around the speed after that. The IBTA, which is the InfiniBand Trade Association, announced that the next speed after 100 gigabit per second is going to be 200 gigabit per second, which is basically using 50 gigabit per second per lane in a 4-lane port. And we already started to work around that. Looking on the 200 gigabit per second time frame, it looks like around the 2017 area. So moving into some of technology developments that we're working on, I'm going to touch 3 of them. One of them is transport services. The second one I'm going to touch is GPU computing and how we can increase GPU efficiencies and what we're doing around that. And then I'm going to talk a little bit about MPI and SHMEM semantics and what we do around those. So just kind of an overview, the latest InfiniBand adapter that Mellanox released is called ConnectIP. ConnectIP is based on a newer architecture. So, the way that Mellanox works is pretty much designing architecture and then take it to several steps or several product lines. The latest one is called ConnectIP, and that based on the 100 gigabit per second architecture. So beyond of increasing message rate to 4x higher levels than anything else that exists out there, which is reaching almost 140 million messages per second, the major element that we increased or added into ConnectIP was a new transport or new mechanisms to provide resources for communications between processes. The new transport is an add-on to the InfiniBand specification that I assume that will be published probably in the next year or something like that. Before I'm going to go to the transport from a bandwidth perspective, results that came from Ohio State University, from DK Panda, which is one of the, I would say, leading MPI developers. He testing the multiple generations just to give you capabilities of what ConnectIP delivers today from a bandwidth perspective. Utilizing its 2 ports of FDR and looking into the Ivy Bridge. So there is a Sandy Bridge platform and Ivy Bridge platform. With the Ivy Bridge platform, the ability to achieve more than 12 gigabytes per second from a single adapter, and then more than 24 gigabytes per second from a dual adapter, which enables to get much more data in and out from a server, And definitely when there are more compute elements within a server, and definitely when you're using GPUs, that's become critical. Now, going back to the transport service, one of the main issues of interconnect technologies is that the resources that the interconnect needs to provide for creating communications between processes typically depends on the system size. And it's something that is true for any interconnect out there. While it's something that makes sense for hundreds and going into the few thousands of nodes, when we're moving to the tens of thousands and hundreds of thousands of nodes, and right now there are, for example, an RFP out there in the US for a system called or named Coral, which is planned to be built in a 2017 timeframe, and this is part of the development toward Exascale system. So that's probably going to be the system before the Exascale that the American government is going to fund. And those systems are looking at tens of thousands of nodes in order to achieve much higher performance levels than today. One of the main issues is how you disconnect the amount of resources that you need to allocate for communication between processes and the system size. And that's something that Mellanox had worked on for the last, I would say, 2 years with several partners. And at the end, we designed a new transport, which is called dynamically connected transport, which has been implemented in the latest InfiniBand card from Mellanox, and will go into the InfiniBand spec. That transport used the concept of having a dynamically set of resources in each of the adapter cards that is set for what the server can do. At the end of the day, a server capability or the concurrency of what the server can do really depends on the server's capability and not the system size. And if you are able to enable resources for process communications, which depends on what the server can do, then those numbers are going to be constant regardless of the system size. And that's exactly what the new transport does. You see here comparisons of memory footprint that needed to be allocated for managing the networking side. And you can see the developing over time. So going to tens of 100,000 of nodes, if you look on technology that was released in 2002, then you need to allocate it so much memory for just managing the interconnect that it's not feasible. Throughout the time, there were multiple development, namely shared receive queue and XRC, which moved into sharing resources between processes and reducing the total amount of memory footprint, but still it's what really tied to the system size. And then the new transport eliminate the connectivity or the relationship between system size and resources. And it's something that's going to take us into the Exascale capable systems. Going into the GPU side, one of the things that Mellanox worked with NVIDIA for a couple of years, and now we're taking that and start working with AMD on the same concept, as well with Intel on Xeon Phi, is that when you build a server, there is multiple PCI Express devices you can put on a server in order to increase the server capability. For example, you put a GPU card on a PCI Express slot, and then you have also an interconnect card on another PCI Express slot. So you can have multiple devices on the same PCI Express root complex. The question is how those two devices are going to communicate one with the other. Previously, all communications went through the host memory. And for example, when you have a GPU card and you're running elements on the GPU, in order to take data from the GPU memory out to the network, sorry about that. So the way to take it out to the network or to another GPU was moving the data to the host memory, which created a lot of overhead. So the idea was looking on devices on the same PCI Express root complex and enabling peer-to-peer connectivity between those devices. And when you enable peer-to-peer connectivity between those devices, you can move into moving data directly from the GPU memory to the network to another GPU, and vice versa. Now, it doesn't need to be a GPU. It could be an FPGA, or it could be memory, or it could be a flash device. It could be multiple things. Motivation was to look into devices that sit on the same root complex, on the same PCI Express root complex, and enable direct connections between those two. Now, with that element for the GPU, which is called GPU Direct RDMA, the benefits are huge. And I'm quoting again data from DK Panda from Ohio State University, where he measured latencies between GPUs, as well as bandwidth that you can get out from GPU, and moving to a direct connection using a peer-to-peer of the PCI Express, it was able to show that there is almost 70% reduction in latency. Now, he also modified its MPI in order to be able to run MPI on the GPU. Because previously, MPI, take into assumption that the entire buffer, all the buffers in the host memory. And it was something, if there was something in the GPU memory, it had to be copied to the host memory. He modified the MPI to look into a GPU memory as extension to the host memory. So now buffers can be in the GPU memory itself. And the ability to move them directly out with GPU Direct RDMA reduced the latency of that by almost 70%, and increased the bandwidth in nearly 5x from the GPU. Now, we're taking that one step further. There is a development that we're doing with a couple of universities in Spain. One of them is the University of Valencia, where the idea here is to move GPUs to become more of a service, or more as you look on storage today. So today, you can, when you put storage on a cluster, you can decide if you want to put storage on every node, or you can have a centralized storage somewhere. And then all the compute infrastructure is going to be connected to the centralized storage. So storage is pretty much a service. For GPUs or accelerators, the situation is not like that. If you want to run a GPU application from a server, you need to have a GPU in that server. And if there is no GPU in that server, you don't run GPU application from that box. So GPU is not a service. The idea around this project is to make a GPU the service, in the sense that you will be able to build a GPU cluster, or put GPUs in some of the nodes, and then be able to go from any compute node and run GPU applications from that node. The concept is very simple. What we created with the university is a virtual GPU software plugin that from one side captures all the CUDA calls, and from the other side goes to the fabric, through the fabrics, find a GPU somewhere that is connected to the system, and then allocate it, use it, and then release it. Now, it works very nicely, but it really depends on the interconnect capabilities, because if it takes a lot of time to reach the GPU, you'll probably better run your application on the local CPU. But if you have a very low latency and you have the right bandwidth to the GPU in the network, then you can really achieve a very good performance. So some of the results that they released, on the left side, you see a bandwidth graph that shows you that with the latest InfiniBand speeds, the bandwidth to the GPU is very, very similar to the bandwidth within a box. So the GPU, it seems to the application like it sits in the same server, which is a good thing. And then on the right side, there is an actual application that they've run to calculate metrics. And you see there is like 4 bars there. The purple one is the performance that is being done on a local GPU on one server, on the same server. And then the green one is what happens if you're running the same, but now the GPU is located somewhere else in the network. But you have a high-speed connectivity to it. And with that, you see that the results are very, very similar. Now, if you're running on CPU only, the performance is much higher, of course. And if you're running on a slow network, which is a red one, then the performance is even worse. Now, that development, provides a very cost-effective way to build GPU clusters, in the sense that if you are planning to run GPU applications, but you don't want to put a GPU on every server, then you don't have to anymore. But still, you can run an application from every server. So if there is any interest to take or to get the software from those guys, you can meet me at the break, and I can connect you to the folks from the university. One last item. I have like 10 more minutes, right? Okay, so I can speak slowly. One last item that I wanted to talk with you is around few of the operations within communication libraries, such as MPI, SHMEM, PGAS, as well as UPC, or Berkeley UPC, and some of the work that we're doing around that. In those communication libraries, I guess you probably know that even better than me, there is two scenarios of communications between processes. One of them is point-to-point, where a process talks with another process directly. And the other way of communicating is using collective operations, which consists of many processes communicating together. One of the main issues around collective operations they are sensitive to system noise and jitter. In a sense of, if there is a delay in a point-to-point communications, that's fine. That's gonna just impact the two processes that are talking with one with another, but will not impact the entire system. When we talked about collective operations, those collective operations covers the entire processes in the system, and therefore a delay within one process will delay the entire system performance. There was a DOE-funded project that both Oak Ridge National Lab in the US, in Tennessee, and Mellanox were involved into looking how to minimize the effect of system noise and jitter on those communications. And it's definitely, again, looking into larger infrastructures and what we can do there. The end of the project results in developing a new technology that moved the management of those collective operations, either MPI collective operations or OpenSHMEM collective operations, from the CPU to the network. And developing a new capabilities on the adapter cards, including adding floating point and integer capabilities into the network itself to be able to do data reductions there. Once you move those collective operations from the software to the hardware, then you can really minimize the effect of system noise and jitter, because now the CPU will not impact that. And you can see it's a very kind of simple example here. On the left side, this is an ideal situation of doing a collective operation within an application where you see an example of few processes, two processes communicate each time, and then there is a combination of the data into process 0, and then there is a broadcast back to the entire processes. This is like a simple recursive doubling algorithm. The impact of system noise, and it's just, if you just even have a system noise in one of the processes, that's going to delay the entire process. So entire collective operation is going to be delayed, which means that the entire applications will be delayed because of system noise and jitter that can impact even a single process. When you move those elements outside of the CPU to the network, this is something that does not impact by a system noise and jitter. And you can dramatically minimize the effect. Now, even further than that, as part of MPI 3 development, and the spec was voted, and I think now there is some MPI developer that start to bring the MPI 3 capabilities into MPI. So we should expect probably this year to start to see MPI 3 out there. As part of MPI 3, there was a development for asynchronous collectives. So today, collectives are synchronous in the sense that once you start an operations like that, you will wait till it ends before you do something else. But with asynchronous collectives, you can start an operations and then move to do something else. And the motivations to do that was to enable overlapping between computations and communications. So today, if you're doing an asynchronous synchronous collectives, you're going to do the collectives, you're going to wait till it finishes, and then you're going to do the communication again, and then move forward. So you work in one after the other. When you do asynchronous and you can start the collective operations and then move to do something else, you can start moving to do overlapping between compute and communications, which means you can dramatically reduce the runtime. Now, the only way to do something like that is if the CPU element will not need to do one of those things. Because if the CPU will do the computations and communications, you're still doing one after the other. Now, with MPI 3 and asynchronous collectives, you can take the network element one and move that to the network. So now you can start the collective operations, have the network manage that, and then the CPU can continue doing communications with the asynchronous collectives. And you can achieve very high level of overlapping. The graph here is a testing from Oak Ridge National Lab looking into how much you can overlap between compute and communications. The 10% line there is if you're running everything on a CPU. So you can achieve a little bit of overlapping, but it's in the 10%, so it's negligible. And then when you move the collectives into the network, now you can start the collective operations, initiate it in the CPU, and then have the network to run everything, and you can achieve nearly 90% of overlapping, which means there is a potential to reduce the application runtime in a very high level. Now, in order to implement that, we had to develop new things into the network and teach the network to do new things that the network didn't know before. For example, network knows how to do send operations or sending data or receiving data. The network doesn't know what wait means. And collective operations includes the term of wait. For example, you send data to process 1, you wait to get data from process 2, and then you send data to process 3, and then you wait to get data from process 4, and so forth. This is a recursive doubling algorithm. So one of the things that we added into the network is ability to wait for data before you do something else. So there is a sequence of capabilities that you can program the network to do.
So it can deadlock by waiting?
No, it doesn't deadlock for waiting, because the waiting is for receiving data from another process. If something happened for that, there is timeouts and things expire, then there is no deadlocks there. But it's the same thing that you need to handle from the software side. Because from the software, you do the same algorithm itself. Now, the ability to program the network, we're using that for the collective operations. But you can use it for other things. So you can program the network to do things, not just for those communication libraries. As well, we also moved ability to do integer and floating point operations into the network itself for the data manipulations. And that's another thing that you can use not just for collective operations. So if you have ideas of ability to program the networks to do sequence of operations as well as data manipulations, this is a technology that you can use for that as well. Going summary, and if there is questions, I'm happy to take them. Mellanox is a company that really drive the development of the fastest interconnect technology out there. From a technology capabilities today, we're around a generation ahead of anyone else or the competition out there. And our goal is to continue to drive that as fast as we can. I think there is an interesting shift today within the market. Probably you heard that IBM sold their x86 portions to Lenovo, and they're going to start focusing on power CPUs. ARM CPUs are getting into 64 bits. So while covering all the handheld devices, and my phone that just rang 10 minutes ago, they start to move into the data center, and we start seeing 64 bits of ARMs out there. There is a project in Barcelona Supercomputing Center, which they build a small ARM cluster and are trying to work and see what they can do with it. So we're going to see probably more options out there for CPUs. There is x86. AMD are doing very interesting things around that. IBM is going to push power. They're supposed to release Power 8 at some point this year. Then we're seeing ARM. So multiple favors, multiple things. There is a lot of things that can be done which weren't be able to do before. From the Mellanox side, our goal is first to drive the speeds, move as many offloads into the network, because that's the critical element. Make the network a smarter element. And then supporting all those platforms. We already demonstrated support for ARM last year. There is also support for power, support for x86, so supporting all CPU platforms out there. I'm on time, I think. If there are any questions, happy to take. If not, I'll be here.
What happens with debugging?
In the sense of?
It's hard enough to debug these programs when they run the CPUs. Now the pipelines
Right. Right. So one of the things that we do provide is do debugging tools. Now there is ability to, all those features and all those offloading in the network are not black boxes. They are white boxes. You can get a lot of information about their states and what happened, and you can go and do it again if you want to debug things. Some of the tools exist already. Some of the tools are based on open source, and there is open source elements there. Some of the tools we incorporate in a management software that we call Unified Fabric Management, or UFM, which people can use either as a GUI or CLI in order to look into interior states of the fabric. And if there are specifics, and we are working with some of government agencies around the world for specific things that they need to know. So you can do the debug and look into things.
In compilation, who decides what happens where?
In the sense of?
The HCA versus on the CPU?
So it's your, pretty much it's your decision. For example, the ability to run collectives on adapter doesn't mean that you can choose not to run collectives on adapter and run it on the CPU. That's what you're asking.
So the program actually specifies and writes to pieces?
Right. So from a program perspective, so first you can choose it from the MPI. So the motivation is to make sure that programs that runs on top of MPI or SHME PGAS will continue to run either way. And within MPI itself, there is libraries that you can choose to dynamically link to it, which will move the things to the hardware or to the software. Now, if you want to control it, you can control it. MPI, it's an open source, and you can decide which way you want to run and choose. Yes?
You talked at the beginning about 10,000 processors. At least what I've seen in a lot of centers, when they have 10,000 processors, they don't tend to give it to one person. They tend to say, okay, we have 100 people who are using 100 processors each. How does that affect efficiencies, other things?
Yeah, so first, I talked about, I think, more than that. The example of NASA was 20,000 nodes, and each node has dual sockets, multiple, so it's much higher than that. Right. So first, in some of the systems, there are several applications that people run on the entire system, because they need those elements. From others, we are part of, for example, many of university systems where they host many people on it and they modify it.
Ames, for example, they have
Right.
many people using it.
Right. Now, you can allocate smaller portions of the system, so running on much fewer sockets or much fewer number of processes. The thing is that within the network, if you're talking about the network, you can allocate and create quality of services. So you can choose quality of services for different users, for example, for different applications, for example. And within the network itself, you can create virtual tunnels, which means that one communications of one applications, even that it goes on the same wire. Motivation is to run everything on one wire, right? You can run storage and compute and management and all those processes on one wire. With having virtual lanes and the ability to do quality of service, then you can distinguish and separate between those elements, and no person will not interfere with another person running on the same system.
It doesn't decrease the efficiency of the machine.
It's first, running on a single wire does increase the efficiency of machines. Meaning you can definitely install multiple networks and run them in parallel, but that's becoming too expensive and you don't need to do it. When you have the needed bandwidth, which is what you need to get out from the server, then yes, you can curve the fabric into multiple things and put the quality of service, then each person will not interact with another one. Thanks for the question.
And is that what you would do with the remote GPU stuff then? Because I imagine if you wanted to do it, you would pile a load of GPUs in one box, right?
So first you can pile GPUs in one box, right? And then you need to make sure that you have enough bandwidth in and out of that box, of course. That's one option. Another option is that you can decide to put GPUs on some of the servers and some you don't.
Yeah, because it's a lot of PCI Express things, right? You use them
Right.
and then the GPUs use them.
Right, because then you put PCI Express. So there are boxes that are very GPU dense. In a sense, you can put tens of GPUs in one box, and then if you have enough throughput in and out of the GPU box, that's it. That's what you need. So you can decide not to put one port, or maybe put a couple of ports, or maybe more in the GPU. But once you leverage from that, it's much more cost-effective to have a single box than putting a GPU in every server out there and be limited with what you can do. So just to make sure that I'm on time, if there is other questions, I'll take it on the break. Thank you very much, guys.